So today we'll investigate part two of the linked list that we created where we were able to insert data at the front of the list and at the back of the list. What I would like to design today are some functions that will test if the list is empty or not, and also give us the size of the list as to how many members are in the list. Then I will conclude that for this part with a generation of an index, which means I'm going to add another attribute to the list right here. So we go over here where we had a payload, and then next here we're going to have a key here that will be of type integer that will be unique to that payload. So that way for the next part, maybe part 3, if time permitting, we will have another function for deleting a node or searching a node based on that index key. So that is my main objective as to how we're going to be moving forward with this. So at this stage, I would like to keep my application the way we had it before, with minimal changes, if any. Let's go ahead and rerun this so we can have a starting point where we understand how this application behaves. And let's go ahead and run this. So as last time, we had a menu-driven application here where we were allowed to enter data at the front of the list, the back of the list, view the list, and so on. So if I type 3 right now, we'll get nothing. The list is empty. But I'd like to get the information that the actual list is empty. So I'd like to get a message that says empty list. Okay, so go ahead and let's go ahead and insert something at the front. So this will be the first node. And let's go ahead and we put 77. So if we put 3 here, that message will not appear anymore, but the payload will appear. Okay. So the next thing is go ahead and test for 2 again. Let's put a -1 and let's do 3 again. As you can see, -1 was inserted at the back of the list. Okay. So this is working as we left it last time. Let's do another one. Let's do a 1, put a 99, and then again a 3, and that would be at the front of the list. Let's do a 2 again, and let's put a 0, and that would be at the back of the list. So if I do a 3 again to show, the 0 would be at the back of the list. So everything is behavior as last time. No changes were done to the program, so today we're going to make some changes. So let me do 4 exit. The first thing I want to do is the empty function. So I want to check if the list is empty. Okay, so I will not make any changes here in the application. As we've seen before, we have a switch statement that's based on a menu that we have here. So this switch statement is within a loop that is conditional on the fact that you didn't pick 4. As long as you didn't pick 4, you're going to push data that you entered using the push front function onto the list, right? So we've created right here a pointer of type list called myList. We initialized it to null to indicate that the list is empty. Okay, so this is a quick review of what we've done. So we've used it, again, push front and push back are 2 functions that are within the class list. So let's go over here. So here they are, push front and push back, okay? Where we're passing the actual payload that we want to change. So if we go back to main, this is the payload right here that you entered in main right here, right? So either you did push back or push front, you entered a new a payload, and then with the push back and push front, you created a dynamic node or dynamic allocation memory here, right here for this one, push front. And you did the same thing here for push back and supplied it with the data. It, in turn, used the overloaded constructor that supplied that data as a value, set the pointer next to null, so we have a node that's pointing to null. Then either you're doing push front or push back, then the key here, if you were doing, for example, push front, go ahead and move a pointer, in this case I called it last, all the way to the end of the list, and then link the node based on what last was pointing at. If you were pushing back, you're simply inserting that new node behind the head. And that was the, so depending if the head was null, then the node will be it that you just created. That will be the head. If not, that means there's data in the list. You will go ahead and put the node behind the head and move the head accordingly, which means the head now is the address of the new node. Okay, so that was basically the basic strategy for it. The printing was pretty straightforward. We had a loop here that went through the whole list and moved a temporary position pointer here to step us through the list content, basically the payload right here. And the key ingredient to move forward within the loop was this statement right here that moved this pointer that we initially pointed to the head of the list. Okay, so now I would like to design a function. So let me break it up here a little bit. So these are going to be my constructors just as a review. And so we have a default constructor here. We have an overloaded constructor. These are going to be my mutators. Okay, and these here, in case I have more, these will be my accessors. Okay, all right, so in my case, I would like to have an additional accessor method that returns a Boolean that will tell me if the list is full or not, or I'm sorry, if it has data or not. So we're going to do that here. So we're going to do bool. And we're going to call it, oops, bool, not boo. Okay, so we're going to call it is empty. And we're going to do the same thing with print list. So the strategy will be fairly simple like this. And I'll make it a const as well. So that way we'll not make any changes as we do this. So let's test this one out and see how it works. So first, we're going to have to design it. So as you can see here, I did a prototype for it. And so let me just save here. I'm going to go to list here. Let me break things down here. So we have our constructors used to creating, so we preload here. So these are our constructors. Okay, so we're modifying our code a little bit. So I'm just adding comments at this stage. These were our mutators. Okay, so just separate them here. And then these here were our accessors. Okay, so for the next accessor that I want a bool list. So within the scope of list, and we're going to look for is empty right here. So right here, and it will take list and then create a pointer called head that points to the actual beginning of the list that you supplied. Again, const, so we're not going to make any changes to the attributes of the node itself or the list itself. Okay, so we're going to go back here. All right, so what do? We're going to do something very similar to the print list. We could simply, right? I'm writing this from scratch, so let's bear with me on this one. We could simply say, if the head is null, well, then your list is empty, right? Because if you think about it, in the code itself, you initialize the list to null. The moment you wanted to create anything or print, right? So in the print, we're going to check if the list is empty. We're going to do it in the print list. How's that? Inside of it. So I'm not going to, as I said, I'm going to try to not modify the application itself. So in the print list right here, this function, I will display the result of is empty. Okay, so what do I want is empty to do? I want it to return Boolean true or false, depending if there's anything in the list. So I could do something like this. If head equals null, well, guess what? Return true, right? The list is empty. If it's not, return. So the code for this was a lot easier than I thought. Return false. And we can test it out. So where am I going to do it? I'm going to do it right here in the print list. I'm going to add a call to this function. Okay, and let print list handle it for me. So if, now we know that isEmpty is going to return Boolean. Okay, so isEmpty, and then you're going to supply it with the actual head that you just have right now, right there, right? And if that's true, then cout, the list is empty. Okay, so if that's true, then the list is empty. If it's false, do nothing, keep going. So I'm trying to see the logic here if this will work. All right, well, let's try it out. Okay, so we've got an extra print statement here. So you rebuild all here, just make sure it works. We're going to go back here and start and just basically run it from here. So compile and run. And I'm going to hit 3. And sure enough, the list is empty. Okay, so now let's put something in the list and let's hope the list is empty does not appear. Otherwise, we got a boo-boo, right? So we're going to hit 1. Let's put a 77. Let's do 3. Good, the message doesn't appear. So it's filtering it out. We're doing well because you're not passing null anymore over to the print function. Let's do it again for inserting to the back. Let's see if there are any anomalies. I don't think should be. I will restart this program, just double check. And I will insert a -1, do a 3 again, right? Looks good. So I'm going to do a 4, rerun the program, and insert at the back. So let me run it again. So I'm going to do an insert back. First, just to prove that we having isEmpty, let's do a 2, insert back 88, and then do a 3, and we're good. So always make sure that you check all possibilities before you call it a day. So we now know it works. The message will appear, isEmpty, will work, and we strategically positioned a print statement right here based on the fact that head is null. Okay. Could I have done all of this stuff here if head is null, the list is empty? Yes, I could have. But I'm giving myself the flexibility of having this function ready for other uses, not just for the print list. So the key behind it is I want it to be a public interface right here where I could use it later on for other things. How about the count? Finding out the size of the, and again, it could be internal. You could do an interface one as well right here. So we're going to do one that returns an integer, right? And it tells me how many items are in the list. So maybe something like this, int. You could say list size or simply size, okay? And pass list as a pointer, right? So you're declaring a parameter as a pointer, you're passing a reference, and const. And let's see if that will work for us. And this will simply return the size of the list. So let's save that. Let's get over here. So we need some sort of accounting. So we're going to do that one right here. And that would be an int. Let me just move, if I could move a little further up. List. And this would be size. Oops. And it will take list asterisk head const, and then we're going to set up a counter. So int count, make it equal to 0, so reset it to 0. So if there's no data, it will simply be 0. We're going to be returning count at the end, so return count. So that's my strategy here. So we're going to do something where we're going to step through the list. Well, we're going to do it like the print list. So maybe a temporary pointer, list star position. So very similar to the print, except I'm not going to print here. I just need a number. Could I have done all that while I was printing? Absolutely. Could I have done that while I was inserting and have a static data member that keeps track of my numbers as I enter front or back? Absolutely. But I like it to be separate. So that way you can query at any time, use this function at any time. So list position equal head, right? So we want to start here. So we're going to set the pointer position to the head of the list. Okay. And we're going to do a while loop here. And we're going to say position is not equal to null. And what we're going to do now is a couple things. We could set the counter. And while we set the counter, so we know that it's not null, so we have some data. So count plus plus will be a good idea, so increment it by 1. Now, once you increment it, you need to be able to get out of this loop. So the way to get out of this loop, just like we did with the print statement, is position, equals to what you're pointing ahead of you, position, and dereference next. That means the next address or the next object or the next node. Okay? All right, so we now know that we can actually print or return some sort of a count. Well, the way to test it, we could always test it in the print statement because remember, I do not want to make any changes to the application. So I simply, when I call print list, I wanted to do both things. Check if it's empty, give me a quick rundown as to how much data or how many nodes are in there. I can take advantage of this if statement right here that I have here. So if it's empty, yeah, go ahead and empty list is empty. If not, so else, then go ahead and call this function or go ahead and print cout, right? There are maybe something like this. And then call the function here since it's going to return size and then give it the head that's in there. That means the starting address, nodes in this list. And then a /n. Let's see how this works. Okay. All right, so I'm just going to hit an enter here so we can see the separation of the two logical blocks that I have here. This simply will check if my list is empty. If it's not, go ahead and print the size or how many items are in the list. Okay, and what I did here is already stepped through all of this to figure this out. Now, could we have done it after we printed everything at the end, printed the list? Absolutely. So what's the point of having a function size? Just in case I want it by itself, and I don't necessarily need to print anything. So remember, your application that's in here is a test application. I need a lot more flexibility than this application. So that means whatever I'm doing here, I'm leveraging code for future projects. So that will give me a chance to do a lot more than just printing. So let's save everything and let's compile and execute. Let me just rebuild all, make sure everything is good. And we're going to run this. Okay, so if I have nothing, let's say I have 3. So is empty is good. So we got that. So let me put data in the front. 1, 78. Now let me go ahead and print and see if we get 1. Yeah, there are 1 nodes. Okay. Maybe an else within an else, or maybe an if within an else for plural and singular. That's fine. We could say there's 1 record, whatever you want to name it, but it's working. So let's go ahead and insert in the back. So let me do a 2, and let's do a -5, and let's do a 3 now. So there should be 2 records, right? So there are 2 nodes in this list. Fantastic. So it's keeping track of it. And at the same time, I'm getting the payload being printed in the order that I choose, front or back. Okay. So let's do it again. Let's do another one. And let's put a 99. And let's do another one. And let's put a 100. And let's do a 2. And let's put -4. Let's do another 2 and put a 3. Now let's do a 3 to see what we have. And we have 6 nodes in this list. Let me count there. Sure, enough. Yep. You know, I pushed some in the front, some in the back. So that's looking good. And it's keeping track of how many items are in there. So let me close this. Right. So that is what I wanted so far with this part. So the next part I am going to discuss, or part 3. So this is part 2, and I'm labeling it here, part 2. And I'm going to do another one in a few minutes, another recording, where we're going to add an index to the list right here as an attribute. And the reason for it is I could use that index to identify each record or each item or each node as a unique record. Okay, that's going to have implication later on if I want to use this as part of a database, or if I want to delete a record based on an index. Instead of saying, okay, well, just delete anything with 23. That means if you have several records with 23, then they all have to be deleted. Or did you just mean the first one or the last one? So that could lead to a lot of confusion as to what node do you want to delete. I want a specific physical node to be deleted, identified by its index, like a book and a page number. I want to tear off page 6. There are no other page 6 in that textbook, right? That's exactly what I want to do next time.